In this lecture, we will discuss about wall functions. A function which can relate the local wall shear stress through the shear stress based velocity to the mean velocity, turbulent kinetic energy and dissipation of turbulent kinetic energy is called as a wall function. So where we are using wall function? So wall functions are usually used in high Reynolds number flows. So that we need to know. So by invoking the universal behavior of near wall flows, one can avoid the need to implement or integrate the model equations right through the wall. So if we have a wall, so let us consider this as a wall, and if we have wall normal distance, this we usually call it y. So y is the normal distance away from the wall. Then if you want to find mean velocity at a point yp, suppose I choose a point yp. Okay, let me choose this point. Let me call it as yp. And this is in the range where it is like 30 to 500 in y suffix p plus. It is satisfying the log law condition. The measurements of turbulent kinetic energy, that is TKE, and its budget. You might ask, what is budget of this TKE? You have this turbulent kinetic energy equation. In that equation, if you find each and every term, that is the production, dissipation, transport, advection, all these terms individually, if you balance this, it is called the turbulent kinetic energy budget. So if you find the turbulent kinetic energy budget at this point, this should tell that the rate of production equals rate of dissipation. So that's the point we should arrive at. If we arrive at this, this can be used to develop the wall function which we defined above. So thereby we will be relating the local wall shear stress to the mean velocity, turbulent kinetic energy and the dissipation of turbulent kinetic energy. Here this U plus is defined by U by U tau equals 1 by kappa natural logarithm of E y suffix p plus, wherein this kappa, you know that it is one common constant 0.41. This E is 9.8, which is the wall roughness parameter for smooth walls. Similarly, you can find this wall roughness parameter for rough walls, which you have to use for rough surfaces. So when you use this wall function in a software or a code, usually the commercial softwares, they ask for roughness parameter, where we have to give that value. So this is the basis for that. Then the turbulent kinetic energy K is given by ut square by root of c mu. Epsilon is given by u tau square by kappa y. So this is the wall function for high Reynolds number flow. Also we should note that this wall function developed for high Reynolds number flow, it is for isothermal condition. So if we want to use for non-isothermal conditions, we have to develop valve functions for specific to heat transfer. So again, this valve function based on universal near wall temperature distribution, which is valid at high Reynolds number. It is given by Landon and Spalding in 1974, wherein they gave that T plus is defined by minus T W Cp rho U tau divided by Q suffix wall, which is equal to sigma T comma T U plus capital P sigma T L by sigma T T. So this is the heat transfer valve function. Now we have to understand the different terms in it. So you know that Cp, it is the fluid specific heat at constant pressure. So it depends upon the fluid medium which you use. Then you have this Qw, the wall heat flux. Then you have the temperature at wall, that is a wall temperature. Then you have this capital P, which is called a P function, a correlation function that depends on the ratio of laminar to turbulent Prandtl numbers. So this is the laminar Prandtl number, this is the turbulent Prandtl number. So you know all these terms. The Prandtl number is given by, this is sigma T comma L, which is given by mu Cp by gamma T. So this is laminar or molecular Prandtl number, wherein this gamma T is called the thermal conductivity. This mu, you know, is dynamic viscosity. So this is the valve function for heat transfer problems, and you can use this for non-isothermal flows wherein you have heated surfaces, that is walls. So we have covered valve function for isothermal flows and non-isothermal flows, and we should note that at lower Reynolds numbers, log law is not valid. So whatever we have discussed till now, that is the valve function for non-isothermal and isothermal flow, this will not work. This valve damping function is developed by Patel et al. In 1985. It is done by modifying the K epsilon model for this low Reynolds number flows. The need for valve damping function is to ensure that this viscous stresses take over from Reynolds stresses at low Reynolds number in the viscous sublayer adjacent to the solid walls. So this is the need for the valve damping function. The equations for the low Reynolds number K epsilon model are given as below. So these are the governing equations for low Reynolds number K epsilon model. So you know the relation for mu t. We have introduced one new term F mu here, and we have the governing equations for K and epsilon. Here we have included the molecular viscosity, dynamic viscosity, that is mu here in the gradient diffusion hypothesis term. Also you might find two terms F1 and F2 here in the epsilon equation. So we need to define these functions F mu, F1 and F2. So these are the valve damping functions which are multiplied with C mu, C1 epsilon and C2 epsilon. So these are the constants, these are the valve damping functions. We need to find what are these wall damping functions are. These wall damping functions, which we have referred earlier, are the functions of turbulent Reynolds number. This RET equals velocity scale, length scale to viscosity, which is given by K square by epsilon viscosity, and Rey is given by K power half Y by nu. Lamb and Bremhorst in the year 1981, they came up with the wall damping functions. F mu equals 1 minus exponential of minus 0.0165 Re suffix y and whole square multiplied by 1 plus 20.5 divided by RET, and F1 is given by 1 plus 0.05 by F mu whole power 3. F2 is given by 1 minus e power minus Re suffix t whole square. So these are the wall damping functions for low Reynolds number K epsilon model. We should note that we have used this wall damping functions as products of C mu, C1 epsilon and C2 epsilon. This is in the governing equation or the transport equation for epsilon. So problems might occur when we are integrating these Grant's equations to the wall. The exact problem is like the rate of dissipation of turbulent kinetic energy, that is epsilon, will rise steeply as the wall is approached and tends to an unknown constant value. So usually these kinds of things happens when we use the low Reynolds number K epsilon model. Once we know about what is the problem and we need to use this model in a flow field, we need to have the boundary conditions. So there were a couple of boundary conditions which was given by Lamb and Bremhorst, which is dou epsilon by dou y equals 0. Another boundary condition is Launder and Sharma, which is like epsilon tilde is given by epsilon minus 2 nu dou root of k by dou n whole square. Also epsilon tilde is 0, can be allowed to be used. And we also should note that these boundary conditions will make the problem numerically stiff. Also this nonlinear wall damping function, if we use it, we will encounter difficulties in achieving convergence for the simulations. So these problems and all we should note, and based on that we should properly utilize these conditions in the application. For further exploring about this wall damping functions, one can refer to book or to journal articles, and also to know what are the wall damping functions available. Either you can go to your commercial software or open source tools like OpenFOAM and see what are the damping functions available or what are the wall functions available. You will get to know, okay, these are the varieties of wall functions available, and then you can look into each and every wall function, where it can be used, what are the advantages and disadvantages. Then you can properly choose a particular function for a particular application.